All right, so what I'm going to do right now before I go over the calculations is show you a different way of thinking about these electric fields. Um, and I'm using a simulation on PhET. We've used that several times before. I'll try and post a link later if I remember to. So here I have a single positive charge, and everything around here is empty space. But what the visualization will show you is the strength and the direction of the electric field. So I'm going to drop that here. And now we can see that even though there's nothing at this location, we see the strength of the electric field where it's brightest. It is where it is strongest. And the electric field has a direction. So every charge gives us a field around it, and that field has a magnitude and a direction. And if I move this charge around, well, we see a little bit of a different, relationship here. But essentially, what we're looking at is, um, a field that goes outward from a positive charge. If I swap that positive charge with a negative charge, we see the same idea, right? The field is due to this negative charge is pointed in towards this. And another way of looking at this now, this is a visualization of all, the field at every location. On the other hand, I could just take, kind of have this sensor. Now, the idea of this sensor is that it has a positive charge. And let's say the charge on this sensor is very small. It's not going to really have much of its own field. And it's not enough to have a significant force on the main charge down here of -1 nanocoulomb. So here you can see the sensor kind of tells us, right, the strength of the field, and the closer I get, the stronger that force is. But the field strength has nothing to do with what charge is at a given location. It's the ratio of the force that this sensor experiences to the charge of that sensor. So, since the charge is in there, in the calculation of force, right, we say force, oops, we say that the force, right, is equal to K times Q1 times Q2 divided by R squared. And the electric field is the force divided by, right? So let's say it's the force that this charge experiences. Let's just say it's Q2. Doesn't really matter. Well, if I divide by Q2, now we can see that the field is just due to this charge and how far away I am from it. So if I have a similar charge somewhere else, that similar charge is going to experience the same force at the same distance. And that's why when we think about the force due to a point charge, there aren't two charges there because the other one got canceled out. And these are the two expressions that we use for the field strength. And then this is specifically right here, the field strength due to a single point charge. Now, if I have multiple charges, then I would have to add in those different interactions. So you can kind of see here where I have a sensor. Well, somewhere in the middle here, I would experience no force, right? Because the forces would cancel each other out here, and there would be no field at that location either. Meanwhile, as I go closer, right, I'm going to get this outward pointing field here, outward pointing field here. But kind of at this halfway point, now we can kind of imagine that the reason this is pointing up is because I have one field that's pointed in this direction, another field pointed in this direction, and the sum of those two vectors is just this upward pointing vector. So that kind of helps us to visualize maybe a little bit more what's going on with the field. And then the other thing that we talked about was this idea of electric potential. So potential is about energy, and kind of like that test charge, if this sensor is positively charged, that's how we define our electric field, we should know that a negatively charged object would experience a force in the opposite direction. Well, instead of thinking about field now, let's think about electric potential. So again, I know that electric potential energy, I've got this little voltmeter which tells us, this is energy per unit of charge. But if I have two positive charges and the sensor is positively charged, I know they're going to exert a really strong force when they're close together. And that means that they have the potential energy to push each other really, really hard and give each other a lot of other kinds of energy, like kinetic energy. Um, and again, the force is due to that Coulomb's law. Energy is related to the joules of energy, right? Just like we can think about gravitational potential energy. If this was gravitational potential energy, I'd have more energy as I got further because my force would be going the other direction. Here, I have more potential energy as I get closer because the force is going away. Or if this was a negative charge, and I'm measuring the potential energy, well, now I've got more potential energy when I'm further away because it's the potential for work to be done on this positive charge. And the closer it gets, right, that is a force and in the same direction. That's work being done, positive work being done, not negative work being done. And what the potential tells us is how much potential energy something has per unit of charge. So instead of looking at a field, we can actually look at kind of the voltages. And again, for a single charge, I have very, very low potential around a negative charge, and I have very, very high potential around a positive charge. So if I think about a positive charge, a little positive charge, moving from here to here, it's going to be gaining potential energy, gaining kinetic energy. Right, it'd go flying over here, and it would lose that potential energy. On the other hand, as I got further from a negative charge, closer to a positive charge, it would be gaining potential energy because it's moving against the force direction that it's going to experience. And again, when we think about this potential, all we have to do is think first that the equation, right, we can say that the voltage is equal to the energy, I'll say electric potential energy, divided by the unit of charge. All right. That means we could flip that around and say that the voltage times the charge tells us the amount of electric potential energy that something has. The signs of the charges are very important because if I have, two charges that are the same, right? Two positive charges close to each other are going to have a high amount of potential energy. A positive and a negative charge that are close together, they don't have much potential energy because they don't have that much room to walk or to travel towards each other. All right, the more room you have to travel in the same direction of the force, then the more potential energy you're going to have. So now I want to go ahead and look at the calculations. And just to make that a little bit easier, I think actually I'm going to put that in a separate video.